Okay, folks, good morning. Any questions? Okay, so we don't have any questions. We had our quiz number 5 last time. So let's take a look at the solution for this quiz. We had this forward converter, and a bunch of information was provided about this converter. Let's just highlight the information that we have. Like the number of turns are provided. N1 is 100 turns, N3 is 60 turns. We don't really care about the secondary side or N2 because that's not the focus of the quiz. The input voltage is 48 volts. Also, if you look at the drawings, you can actually extract more information. One of them is that the on time of the switch is 5 microseconds. You can call this duty cycle times T. So we don't have the switching period, we don't have the duty cycle, but we know that the switch is on for 5 microseconds. The other piece of information is the peak value of the current for the magnetizing inductance is 3 amps. And I guess that's it. That's all the information that is provided. And we are looking for instance, draw the voltage drop across the magnetizing inductor, VLM. Basically, we are looking at this voltage. Okay, what does this signal look like? In the first mode, when the switch is on, this voltage is the same as the input voltage. And we know that input voltage is 48, so this remains at 48. Then in the second mode, there is a mechanism to discharge the current of this magnetizing inductance, and that is when this diode over here, I guess it was D3, turns on and applies a relatively large voltage to this VLM, and that large voltage is the input voltage reflected through the N1 winding, reflected to N1 winding through the N3 winding. So in that particular case, this voltage is negative, and it is proportional with Vn. Obviously, it's negative, and this ratio is N1 over N3. Okay, so we have N1, we have N3, and we have Vn. If you put all the numbers, this gives you negative 80 volts. And finally, in the last mode, this inductor is totally de-energized. Therefore, there is no current, there is no voltage drop across this inductor, basically. Let me just erase this a little bit. So this voltage is 0. And then the next cycle starts, and again, everything gets repeated. All right. So this is the voltage waveform we're looking for. Positive, negative, and then finally 0. And that is in agreement with our current waveform because we have a positive slope, we have a negative slope, and then we have 0 slope. Okay? So this is VLM waveform. Then part B is asking about finding the value for LM, the magnetizing inductance. So how can you find that? You can look at basically this current waveform and make a basically argument that I have an inductor, I have applied 48 volts to this inductor, and it took 5 microseconds for the current of this inductor to rise from 0 to 3 amps. So that's pretty much, you have all the information that you need to find the inductor. So that would be basically, you can argue that in an inductor, delta I over delta T is the voltage of the inductor over the value of the inductor, assuming that the voltage is constant, a DC signal. So delta I is 3 amps, delta T is 5 amps. Yeah, I should say maybe delta T lowercase t. 5 micro. The voltage is 48, and we are looking for L. Okay, LM. So So Lm turns out to be 80 microhenries. All right. So that's the value of our magnetizing inductance. Then part C is asking about how long is the duration of Tx? And Tx is already highlighted here with a question mark. It means ultimately we want to find the value of Tx. Now you can ask this question this way. We have an inductor. It is 80 microhenries. How long does it take to push the current of this inductor from 3 amps to 0 if you apply negative 80 volts to this inductor? So pretty much you are going to use the very same equation. You can say now delta I is 3. Delta T is, we don't know. We are trying to find it. The voltage that is applied is 80 volts in a negative way, and the Lm is 80 micro. And then you can find Tx to be 3 microseconds. Or, I mean, there are equations in the notes that you can use these equations as well. Or you can argue that, okay, I started from 0 and I ended up at 0. That means this positive area should be the same as this negative area. Or 48 times 5 microseconds should be the same as 80 times Tx. And therefore, again, you can find Tx to be 3 microseconds. All right, so 2 different ways of finding Tx. And finally, find a value for Ix. And again, Ix is over here. This is when the input current gets negative. We want to see what is the peak value of that negative, basically, current. If you remember the operating modes, basically, when we have this negative current over here, all this current is the reflection of the current of the magnetizing inductance that is flowing through D3. So technically what's happening is, in this mode, this magnetizing inductance current is flowing in here, and therefore it causes some current to go in here, and that would be a negative current for our input current, because ultimately the current is kind of flowing in this direction. All right? So we have it in the notes. Technically, you can argue that this negative value is ILM max. So technically, we are kind of looking at this piece of the inductor, magnetizing inductor current, and just multiply it by -1, and then multiply it by the turns ratio of the N1 and N3. So this peak value or negative minimum value would be ILM max times N1 over N3, and obviously there is a negative sign to it. Okay, so this would be negative. This max value is 3 already given, and N1 and N3 are 160. So this gives you a negative of -5 amps. So that's actually this current value over here. All right, any questions?
There's the same problem which is there on Boston and Blackboard. And the sample homework.
Okay, is this okay? I forgot, but as I said, sometimes I do that intentionally. This was not intentional, but sometimes I do it intentionally in the sense that to encourage you guys to look at those sample problems. Yes, good, thank you. All right, other questions? All right. So we are going to continue our discussion on DC to AC inverters. We are still focusing on the single-phase inverters. What we did previously was we looked at a simple, obviously our topology is something like this. We have an H-bridge. And let's see, having the right date. We kind of have this H-bridge over here. We have 4 switches, and obviously the load and the DC source. First, we looked at the very simple switching scheme and we called it like a square wave switching scheme. And that is, for instance, we turn S1 and S2 on for 50% of the period, And then for the remaining part of the period, we turn S3 and S4 on, and therefore, if you look at the output voltage waveform, it looks like a square. All right, something like that. Then we looked at the harmonic contents of this, and we argue that if you really want to have like a control, some sort of a control parameter in terms of applying a certain amount of power to your load, you can also take advantage of this zero value that you can generate. So we also looked at another switching scheme that applies such a voltage to our output voltage. So there's a little bit of a dead time introduced in the system. During that dead time, we are kind of shorting our load or applying zero to it, and by adjusting this dead time, you can actually control the amount of power that is being consumed by the load, or in other words, you're controlling the peak value, or the amplitude of the fundamental harmonic in the output voltage. So these are called kind of a square shape or a staircase kind of switching schemes. The good thing about these switching schemes are that the switching frequency is not very high. Technically, you can argue that in one period, you're turning the switches on and off maybe once or maybe twice. So it's pretty much good. So if you are trying to, generate 400 hertz in your output voltage, your switching frequency is only 400 hertz, and therefore the switching losses are relatively low. So that's a good thing. The bad thing about these guys are, if you look at the frequency spectrum of, for instance, V out, we have this fundamental frequency that we would like to see, and then we don't have anything for twice that, but 3 times that. We have actually our undesired harmonics, the first undesired and the most actually significant undesired harmonic appearing. So if your objective is to create a very purely sinusoidal signal in the output, for instance in the current, you have to filter out this voltage waveform, and I'm actually showing here the for instance Bode plot of the impedance of that particular filter. That what this filter does is it allows the fundamental harmonic to pass through without any attenuation, but then at this particular frequency you have a lot of attenuation to eliminate the higher order harmonics. Now, designing this filter is challenging because these frequencies are very close to each other. Like, for instance, this number 1 harmonic could be 60 hertz, and the third one would be 180 hertz. So we only have 120 hertz away. These are only 120 hertz apart from each other, meaning that this should be a very steep slope, meaning that the order of this filter should be very high, meaning that this filter is going to be cumbersome, complicated, heavy. Probably you have to use more inductors and more caps. So that's the main actually disadvantage of these topologies. Now we started discussing the PWM switching schemes. Okay, and we introduced actually 2 of them, bipolar and unipolar. And as it turns out, in these PWM schemes, so this would be a square wave. As it turns out, in the PWM schemes, we again have this fundamental harmonic that we would like to see, but the good thing about them is the undesired harmonics are way to the right, somewhere around here, for instance. All right, so nothing appears at 3, at 2, or 3, or 4, or 5. They all appear all the way to the right around MF, which was the frequency modulation index. Okay, so that means the desired harmonic and the undesired harmonics are way away from each other. That means if you design even a very simple filter with not a lot of attenuation, it's very easy to eliminate those undesired harmonics. So this is the major advantage of doing PWM switching. What are the disadvantages? Obviously, the control is a little bit more complicated. You need to have a sinusoidal waveform, you need to have a bunch of triangular waveforms, then compare them against each other, and then make decisions. You're turning your switches on and off more, actually, So your switching frequency is higher, therefore your switching losses are a little bit higher. So these are the two major actually disadvantages of the PWM schemes. The first PWM scheme that we talked about, which we labeled the bipolar, is basically comparing a triangular waveform versus a sinusoidal waveform, and this sinusoidal waveform is actually at the same frequency of our desired fundamental harmonic in the output voltage. And for instance, in this time interval, when the triangular is larger than the sinusoidal, we turn S3 and S4 on, therefore negative Vin is applied to our output voltage. We do the same thing, for instance, here. And that corresponds to this negative part over here. Otherwise, we turn S1 and S2 on, and we apply Vin across our load. So as you can see, our output voltage looks like something like this. It doesn't look like a sinusoidal signal, but we are going to look at the frequency spectrum of the signal in a few minutes. But if you look at the moving average of this signal, you can see that, for instance, if you focus on like this area, you can see this positive area and this negative area are almost the same. So we can argue that the moving average should be somehow crossing, at some point should be crossing zero, and this is the same here. And if you look at, for instance, here, you can see we have a lot of positive area and only a little bit of a negative area. That means the moving average is actually very large. And here you have a lot of negative areas and only a very small positive areas. That means the moving average should be relatively negative, so something like that. So that could be moving average, or basically the fundamental harmonic of this signal that we are going to look. So the signal doesn't look sinusoidal, but it actually behaves a lot like a sinusoidal signal. We introduced two parameters. One of them compares the frequency of the triangular waveform with respect to the frequency of the sinusoidal waveform. And as you can see, the frequency of the triangular waveform is higher. It's usually an integer, MF, and we label this to be MF. And frequency modulation index or ratio, which is a number like, for instance, 17 or 15 or 21 or 35, something like that. The other one is the ratio between the amplitude of these signals, like how much is the amplitude of this signal with respect to divided by the amplitude of the triangular waveform. It's called MA, the amplitude modulation ratio or index. It's usually a number less than 1. So this was all about the unipolar, the bipolar switching scheme, and we talked about another one which is called the bipolar switching scheme, and this is how the logic is a little bit different. So technically what you argue is, let me see. For instance, it's really hard to, okay, for instance, if I am in this period of time, my triangular is sticking out, I apply basically a little bit of a 0 over here. And I do the same thing when this is also sticking out. So I apply a little bit of a 0 over here. Otherwise, I apply positive Vn. If I'm in the positive phase of my reference signal. If the reference signal is in the negative phase, actually I pretty much do the same thing, but instead I jump from 0 to negative V and something like that. This thing is called unipolar because if you only focus on half of your period, you only see one polarity, and that's positive or 0. You don't see negative values. And if you focus on the second part, you see 0 and negative levels. So it's like a unipolar kind of a thing. Now, these switching schemes are a little bit different from each other. The output voltage waveform looks a little bit different. The harmonic contents are a little bit different. So you have to be very careful. If you're using one of these, you should be, like in the end, towards the end of this class, we are going to look at a bunch of tables. When you're looking at a particular table that is giving you the harmonic content of a particular output voltage, you have to be very careful you're using the right table. Like if your switching scheme is a bipolar switching scheme, you got to make sure you're looking at a bipolar table. Or if it is unipolar, you have to make sure your table is a unipolar. Now, for the sake of simplicity in this course, we pretty much focus on the bipolar one. There is no specific reason. It doesn't mean that it's better. It's just a matter of just focusing on one and being good at least one of them. So primarily focus on this bipolar one. Now, we also talked about this graph, and that is on the x-axis I have MA, which is the amplitude modulation index, and on this one I had the amplitude of the fundamental harmonic in the output voltage normalized by the DC value of the input. As it turns out, if the amplitude modulation index is less than 1, I'm pretty much in a linear region. That means, for instance, if I increase the amplitude of my sinusoidal reference signal by 20%, I would expect that I would see a 20% of rise in the amplitude of the harmonic the fundamental harmonic in the output voltage. Meaning that, let me show it over here. So that means, for instance, if I reduce the amplitude of this signal by 20%, for instance, and get a signal like this, and do the modulation, I pretty much can see the same effect here. The fundamental harmonic also reduces by 20%. So this is all this thing. It's like in a linear region, okay? And then beyond that, so if I keep increasing the amplitude of my sinusoidal signal, you can see this sine signal and this triangular signal have less opportunity to cross each other. So we get to more like a saturation region, and then like an overmodulation region first, and then saturation region. So you can see this linear region does not continue forever. If we get saturated and we stay flat, meaning that at the flat area, that means the amplitude of the sinusoidal signal is too large, we are actually switching back or moving towards the square wave basically switching scheme. All right. So this is also, we mentioned that last time. Now what we are going to do is we are going to look at the frequency spectrum of the output voltage waveform. Okay? There is not a kind of a closed form equation that can give you the frequency harmonics of this particular waveform. Numerically, you have to solve it and find out that it looks like this. All right. So what are we talking about here? So we have n here, which is the order of our harmonic. We have the fundamental harmonic here. Okay? And over here, what is happening is we are normalizing all of these numbers with respect to the fundamental harmonics. You can see the fundamental harmonic is 1 or 100%. That doesn't mean it's really 1. It's just with respect to itself is 1. Okay? Then at n equal 2, we have nothing. At n equals to 3, we have nothing. It takes a while until the next harmonic appears, and that appears around m some f, which was the frequency modulation index. So if we select mf to be, for instance, 15, you have no harmonics all the way from 1, you have nothing all the way through the vicinity of 15. And then you can see you have a bunch of actual harmonics. All right? And then you have nothing until you get to the vicinity of 2mf and 3mf and 4mf. So the good thing is it's very easy to filter this thing out because they are very far away from each other. All right. Now, what is the magnitude of these harmonics? There are tables telling us. So that's actually a table like this. So this table is coming from your book, basically. So let's see what's happening in this table. Okay. So I am using m sub a, the amplitude modulation index, as a variable. So MA, remember, it was a number usually less than 1. As you can see, it's like here it's 1, then it's 0.9, and going down all the way to 0.1. Okay? So it means like I'm actually using this as a variable. You know, I'm kind of exploring different amplitudes over here. All right. Let's say we have already chosen MA to be 0.8. Let's say we are just focusing on this particular column, okay? What it's telling us is at the fundamental harmonic at n equals to 1, the amplitude is a normalized value of basically 0.8 with respect to the input voltage. So these numbers are actually normalized with respect to the input voltage. So this 0.8 means V1. Okay, if you choose if you choose MA to be 0.8, okay, and then look at the amplitude of V1, which is the fundamental harmonic. This 0.8 is giving you that it is actually 0.8 times Vn. And no surprises, because we are in the linear region, so whatever MA is, the fundamental harmonic gives me the same thing, and that's why all of these numbers are actually the same, because we are in the linear region. Okay? So that was no surprises. We already knew that. Then it is also telling me that at harmonic that is sitting on the integer of MF, so we are looking at VMF, and the amplitude of my signal is 0.82 times Vn, which is technically this guy over here. All right? The harmonic that appears at MF. We don't even know what MF is, but we know MF is a large integer, like 15 or something. So we haven't even narrowed down MF yet. Also, this number is telling me that at n equals the order of harmonic to be MF plus or minus 2, I have 22%. So, for instance, at MF minus 2, I have 2.22 times 22% of Vn, which is basically giving me this sideband over here. And then at MF equals, at V,
1.5 wrong.
plus 2, I have the exact same thing.
2.5 correct.
So there's a little bit of a symmetry over here, and that means this sideband and the other sideband, in terms of amplitude, they are almost the same. This particular table doesn't tell me what happens at MF plus 4 and MS minus 4. Is pretty much neglected. So, so this table only gives me the particular frequency at the particular harmonic at MF, and then MF plus or minus 2. It doesn't give me beyond that. But this would work pretty much here, because I can see these are much tinier. But if you go, for instance, somewhere here, you can see that all of a sudden this is probably 4 MF plus, maybe 6 or 5 or something like that, and then it's very large. So this table could be useful if you're only focusing on somewhere around MF. There's another table coming from another book. This particular table is coming from a book by Dr. Ned Mohan. I don't know, power electronics or fundamentals of power, something like that. And it's a little bit more comprehensive. So let's take a look at this one. So again, we are using MA as a range to select a column. Like here, MA is 0.2, then 0.4, then 0.6, then 0.8, and then 1. Okay. For instance, for 0.3, we don't have any particular column, but you can take the average values and kind of find it. For n equals to 1, which is the fundamental harmonic, because we are in the linear region, these numbers are exactly identical. Same that we had here. This row and this row were the same. All right. Now look at what happens around MF. For instance, let me just focus on AD, 0.8 again. So you see this number, which is 0.8 0.18. Again, it is telling me that the amplitude of the harmonic at MF is this, which is basically the same equation that the other table was suggesting, but the other table has rounded this 8.18 to 0.82, something like that. So it's basically the same table, only a little bit with more, accuracy. Then it is telling me that at MF plus or minus 2, I get 0.220, which is the same number that this table suggests. But this table, the top table, doesn't continue, but this one does. For instance, this is also telling me at 2MF plus or minus 1, I get 0.314, which is basically these two little guys over here. And then at 2MF plus or minus 3, I get something else, and that is these taller guys. And then 2MF plus or minus 5. So it's actually giving you more information about all of the high frequency content of your output voltage. Then it also gives you at 3MF plus or minus 2, plus or minus 4, plus or minus 6. So we have all these numbers available here. And then even at 4MF. But you can see the numbers gradually damp down to 0, so you don't really have to continue that particular table. So it's a matter of your choice, how much accuracy you want. You can use the top table or the bottom table. The bottom table is already available on Blackboard. I think it's the name of the file is like Mohan's table or something like that. I guess, yeah, I guess something like this is already available on Blackboard. So this is what it is. All right. Do we have any questions so far?
From this graph, it doesn't, it appears that the harmonic at MF has a smaller amplitude than the one at than the fundamental. But from this, these forms, it is that the harmonic at MF appears to be greater than the fundamental.
It depends on which one you're looking at. So you're saying that the harmonic at MF, according to this table, is larger than
Fundamental.
Yeah, it is sometimes larger than the fundamental. You're right. You can see these are all larger.
But from the above that figure,
from this table, you can
above figure.
The above figure. Okay. This figure, what it is telling you is, well, you're right. I'm surprised. Yeah, it shouldn't look like that. So according to the table, this should only be this high. You're right. Yeah, maybe this should be cut out or something. Yeah, you're right. I think this is coming from the book. I'm not sure. But yeah, you're right. All of these are suggesting that, although it depends. Hold on. We shouldn't jump.
MA is equal to 1.
Depends on what harmonic you're looking at. Like if your MA is 1, you can see this is 0.6 compared to 0.1, right? So the fundamental is larger than MF. But if you look at here at MA equal to 0.1, the fundamental is smaller than MA. So it depends on what value for MA you have chosen. If your MA is very large, this is correct. If MA is very small, then it should actually be somewhere around here. So yes.
What about the other frequencies? Are they insignificant or they don't even
Other
exist?
frequencies, you mean like 2 and 3 and stuff?
Yes.
They are 0. They are just 0. Now, I have actually a numerical example on MathGAT. I'm not sure if this one is posted on Blackboard. Unfortunately, it takes a little while to calculate. That's why I started this at the beginning of the class as I was lecturing. So we can actually look at how small they are. So this was actually this file. I did not create this file. There was a graduate student here, Murali, I think his name was, Murali Bagu. So he actually, he gave me this file. He, on his spare time, he has created the file. God bless him. But anyway, so this is a sine wave, triangular wave, modulation. So as you can see again, the blue curve is our modulating triangular waveform, and then the red one is our reference, which is a sinusoidal signal. Then we kind of compared these signals to do our bipolar PWM basically functionality. So actually our output voltage is something like this, proportional with this, because this goes all the way from -1 to 1, but our output voltage is from -Vn to Vn. So it's just multiplied by Vn. All right. Then what he does is he goes with the classic definition of this Fourier series and then tries to calculate these particular harmonic contents. So basically he multiplies the signal by a sine waveform, like over here, and then takes the average value of that. Then again multiplies that by a cosine waveform and takes the average value of that. And he's actually running this experiment for H is the order of harmonic 1 through 40. If you plot them, they look like this actually. All right? So you see, okay, I have a major harmonic over here, pretty much nothing. Then in this particular example, MF has been selected to be 17, I guess so. Let me just double check. Yeah, as you can see, MF is 17 over here. So we have harmonics at MF and MF plus 2 and MF minus 2, and then 2MF plus 1 and minus 1, and then plus 3 and minus 3. Now as you can see in this particular one, some of these components are negative, okay? However, in this graph, everything is positive. Now, why is that? Because it's actually looking at the kind of absolute value of the magnitude, something like that. It only looks at the magnitude, not the phase. Over there, you can see that because if it is negative, the indication is we have a particular amplitude and it's like 180 degrees out of phase, something like that. He does that with the cosine terms as well, and as it turns out, the cosine terms are all this blue stuff, and they're all 0, so we don't really have to worry about the cosine terms. All right. Then I'm kind of here reconstructing this signal. I'm just considering the fundamental harmonic that this spits out, so I'm considering just this harmonic, and also MF, which is this harmonic. And if you just consider these two, you get this red one. As you can see, it's not even close to the blue one. So we have to add more harmonics. Well, unfortunately, if you decide to do so, it's going to take forever. Here is the table for the numbers. And remember, there is some error, some tiny little errors. Like, for instance, here it is telling you that the harmonic at n equals to 1, 2, 3, is -1 point something times 10 to the power of -5. It's basically 0. It's just a calculation error. But the numbers that you obtain here exactly match with that table. Keep in mind, MA has been chosen to be 0.8. So you can see the first one is actually 0.8, which is, okay, which is here, 0.8. And then let's take a look at the second one. Pretty much everything is 0 all the way down to here. 0.22, which is MF minus 2. And we have the same thing here, 0.22, MF minus 2. And then we have another 0, then 8.18, which is actually MF. And we had it here as well. Here it is. And then we should see another 0.22 at MF plus 2, and that's where it is. And then again, bunch of zeros, and pretty much the table is not long enough. The remaining is just 0, okay? So numerically, you can actually calculate and see what they look like. And as the question was, are these components really 0? The answer is yes, they are absolutely 0. But if you numerically calculate that, you may get a number that is very, very close to 0, but it's not absolutely 0. All right, so this, if it is not available on Blackboard, I can post this on Blackboard. If you guys are interested, you can mess around with it. But it takes about a few minutes for this to run and spit out this table, basically. Any questions so far? Okay. So what we are going to do now is we are going to actually use an example to see what all these numbers actually can be used for. In some of our exams, you need to have one of these tables, like maybe in the next quiz. And if that's the case, I will provide you basically this particular table, or I just put it on the board so you guys can see it, or as a second page to your quiz so you can actually have access to it. Obviously, you don't have to memorize it and you don't have to bring it with yourself. I will bring it to you guys. I will make it available. All right. So let's take a look at this example. So this example is all about how to use these tables. So we have this. First of all, let's double check and make sure the topology is the right one. Yes, we have a full bridge inverter, and the switching scheme is bipolar PWM. So please remember, if you're using this table 8.1, it is only for bipolar switching scheme. It's not for unipolar. Unipolar has a different table of its own. And the sinusoidal reference signal that we are using is 60 hertz. It's an indication that the output voltage at the fundamental frequency should also be 60 hertz. So it's like a utility kind of application. And MF, the frequency modulation index, has been chosen to be 21. And MA is 0.8 or 80%. Load resistance is 10 ohms. And the load is an RL load, and there is a 20 millihenry and inductance there. And the DC value of our source is 100 volts. Okay, so all this information is provided. And now we are trying to, for instance, part A is asking about, well, obviously, if you follow this bipolar switching scheme, there's going to be an output voltage and there's going to be some harmonic content to that. The first question is, what would be the amplitude of V1, which is the fundamental harmonic in the output voltage, and I1, the fundamental harmonic in the output current? All right. So you look at this and say, okay, wait a minute. MA has been chosen to be 0.8. It is less than 1. We are in the linear region. Therefore, we are allowed to use this table. And you can either use the table or just say, okay, we are in the linear region. Therefore, the fundamental harmonic is the same as our amplitude modulation index, and they are both 0.8 times the DC value of the input voltage. It gives you 80 volts. So from a 100 volt DC source, you can create a signal that is sinusoidal with 80 volts of amplitude. Now, what about I1? We are doing some sort of a frequency analysis over here. So we can, in order to find I1, I can look at V1 and evaluate the magnitude of the impedance at that particular frequency, and then divide them by each other using Ohm's law, and then find I1. So technically, you can argue that IN, the magnitude or amplitude of the harmonic of the current at number n, harmonic number n, is Vn over Zn. And Zn is just the magnitude of the impedance evaluated at that particular frequency. And remember, our load is just a resistor placed with an inductor. Impedance here is R. Impedance here is JL omega. So your total impedance, they are in series. So the magnitude would be okay. Now, because we are kind of sweeping across n as the order of our harmonic, we are also going to add an n over here as well. Because omega is not basically a variable. All right, and that's all I have over here. So for the first part of the problem, I'm focusing on n equals to 1, so I'm only caring about r squared plus L omega squared, something like that. So this is r squared, this is L omega squared, and altogether it gives me 6.4 amperes. So this is the magnitude of I1, which is the current in the output side at the fundamental frequency. All right. Now, in order to show how effective this PWM switching scheme is, we can actually look at, for instance, I sub MF or I sub MF plus or minus 2 and see how smaller they are compared to this 6.9. So if you want to do, for instance, total harmonic analysis, total harmonic distortion analysis, you can see PWM is much better. And that's what we are doing. We are looking at part B, power absorbed by the load resistor. Even if they said power absorbed by the load, we only had to focus on the resistor because we have an inductor. There's no power absorbed by this inductor. So in order to find the power absorbed by the load resistor, what we have to do is all right, so this is what we have on the output side. Power. Remember, the power dissipated in a resistor is the value of the resistor times the RMS value of its current squared. So what we have to do is find the RMS value of the output current. Now, remember, our output current has a bunch of harmonics, so we have to consider all of these harmonics in this RMS calculation. So we have to do it like this. So this is the contribution of the fundamental harmonic. The contribution of the next harmonic, which is MF minus 2, then at MF, and MF plus 2, and we can keep going, but as it turns out, if you look at the numerical values, they get pretty small, and that's the indication that we should really stop here because the higher order harmonics do not really contribute much in the output current waveform. All right. All right. We already found this guy. Or at least we've just found I1. So I1 RMS would be, so let me just write it over here. I1 RMS is just I1 over the square root of 2 squared. And we found I1 already. I1 was 6.39, okay? Plus, and what about IMF minus 2? Let me just do it over here. And by the way, these are all RMS. All right. Well, obviously getting the RMS value of the signal if you have the amplitude is very easy, just a division by the square root of 2. So now what we have to do is we have to find the harmonic of the current at what frequency? At MF plus 2 times the fundamental frequency. So this would be something like this. So in order to find the harmonic of the current, we look at the harmonic of the voltage, then divide that by the magnitude of the impedance evaluated at that particular frequency. All right, so let's do that. It doesn't matter if you replace MF to be 17 or whatever it is this 19 or something? Your MF is actually 21. And the numerical value of the actually MF doesn't really matter. As long as MF is a large number, that table holds. So technically, we have to use this table, and as the indication is, MA is 0.8, so we got to use this column over here. And for instance, I was focusing at MF minus 2, which gives me this 0.22 over here. So this would be Vn, whatever the input voltage is, then the rest is just the matter of plugging the numbers. I don't know, let's see, R is 10. Actually, I just said that the value of MF doesn't matter, but it does matter over here because we have to plug it in. MF minus 2 is 19 times L, 20 milli, times omega, which is 2 pi 60. And then take the square root of the whole thing. All right. So if you numerically do this, you're going to end up with all right. So you can see that your fundamental harmonic current in terms of amplitude was 6.39. The second harmonic is only 0.11. All of a sudden, it's much smaller, which is good news. That means we are doing a good job. If you're only focusing on the current waveform, we are doing a good job filtering the undesired harmonics out. So this was for IMF minus 2. You can do the same thing for IMF RMS, and that gives you 0.36. Then IMF plus 2 RMS. Now remember, when it comes to the current, IMF minus 2 and IMF plus 2 are different because for IMF minus 2 you place 19 over here, for IMF plus 2 you place 23 over here. So we expect this to be even smaller, and that turns out to be 0.09. Okay, and obviously the units are all amperes. All right. So we are not going to continue, for instance, for 2MF plus 1 or minus 1 because this number grows to 41 and 43, and they are very, very small values. So it's actually a good indication that it's a good place to stop. So you can do that, and it turns out to be, so in the end you have to basically add them up all together. So this would be we're not going to continue this, and this gives you let me just give you in terms of power values. The fundamental harmonic gives me 204 watts. The harmonic at MF minus 2 only gives me 0.1 watts. The harmonic at MF gives me 1.3 watts. It almost gives me about 205 watts. So as you can see, even though our output voltage was not sinusoidal, our output current, we don't have a graph for that. Maybe next time I can do some simulations and bring them over here. Our output current is pretty much sinusoidal, and the fundamental harmonic is the dominating term in that. It is giving us 204 watts out of 205 watts that the converter, that the load is consuming. So it's actually a good deal over here. And you can see you're doing a good job in terms of filtering, and your filter is not a very fancy filter. It's just a resistor in series with the load. So actually your load is acting like a filter of its own. You don't really need to add any extra filters to the system. All right, so this was a numerical example of how to use that. So pretty much we only focus on this little area over here. We did not really use these numbers at all because they are small to begin with. Then they get divided by a MF plus 2 or minus 2 MF plus or minus 1, and that actually gives you almost 0, so you don't really have to bother with them. And part C is asking about total harmonic distortion. So remember, total harmonic distortion was defined as take all of the undesired harmonics, consider only focus on them, and find their RMS value, and then divide that by the RMS value of your desired part of the signal. So remember, I1 RMS is the desired part, so it comes here, and then top here are all of the undesired contents, so like I19 RMS, I21 RMS, I23 RMS, those kind of terms. So we pretty much have all of these numbers over here. Again, we have to use them, and if you do so, it gives you about 8.7%, which is actually quite a good deal. If you look at the total harmonic distortion, we had a numerical example for a square wave inverter, and the total harmonic distortion was about 16 or 17%. Here you can easily see that you can even reduce it almost to half of what it was by switching from a conventional switching scheme of a staircase to a bipolar PWM switching scheme. So that's a good thing about PWM switching schemes. They always give you a small value of total harmonic distortion in the current. Now remember, if this is, for instance, was an electric motor that you were trying to drive, total harmonic distortion in the current is an indication of the amount of vibration in your electric motor, or amount of torque vibration, or harmonics in the torque. So ideally, an electric motor wants to be fed with a current that is purely sinusoidal. So the closer you are to the sinusoidal current waveform, the less vibration and torque, basically torque harmonics you are going to have in your electric motor. So PWM inverter is better than a square case when it comes to driving electric motors. Now we have another example of using this table. Do we have any questions before we get to the other example? Okay, we don't have any questions. And please remember, it may look a little bit easy, but you really have to practice using these tables. You may get confused between what was MA, what was MF, which column should I look at, which numbers should I use, those kind of things. Now this example has been, as it turns out, has been a kind of a confusing example. So I actually have it over here. I'm just going to cross it out and look at the next page, which is basically the same thing. All right. So this is more like a design example. In the previous example, everything was kind of preset. We just had to do a numerical analysis to find, for instance, what was the total harmonic distortion. Over here, it's more like a design example, and it is asking us to find MF, okay? So us as the designer should decide what value for MF we should choose, having in mind that the total harmonic distortion of the output current should be maintained below 10%, okay? All right. So first of all, it is a bipolar. Again, because it's a bipolar switching scheme, I am allowed to use that table. PWM inverter. When we focus on the output voltage at the fundamental frequency at the output voltage, at the RMS value of that fundamental frequency of the output voltage, we are looking at 75 volts RMS. All right? So it's like you're trying to send some power to some sort of an AC grid which has a 75 volt kind of an RMS value. It's imaginary though. And the frequency should be 60 hertz. The DC voltage that we have available is 150 volts. And the load is 12 ohms. And the inductor is 60 millihenries. And we have to keep the total harmonic distortion in the output current to be below 10%. Because we are using a PWM switching scheme, it makes more sense, always makes more sense to keep it under the linear region, okay? And actually the numbers that we are selecting is an indication of that. So remember, we looked at the amplitude modulation index, which was the ratio between the amplitude of the fundamental harmonic in the output voltage divided by the DC value of the input voltage. We have V1, we have Vn, we can easily find MA. The trick is we shouldn't directly use 75 because 75 is the RMS value of the signal. So in order to get the amplitude, there's the square root of 2. So you can see that MA of about 0.7 will do the job for you. It may not exactly speed out 0.7, but you can actually keep MA around that and use that table. Because this table doesn't give you a column for instance, MA is equal to 0.707. We don't have that column. All right. Now that we have MA, let's look at the magnitude of the fundamental component in our output current, or I1, which is V1 over Z1. V1 is 75 times the square root of 2. Again, remember, all of these are amplitude values. Z1 is the impedance of the load evaluated at the fundamental frequency, which is 2 pi times 60. So this is our omega. Technically, n is equal to 1, and this is our L, and this is our R squared. So we have everything, and as it turns out, I1 is 4.14 amperes. All right, and remember, this is amplitude. All right. Now, when it comes to total harmonic distortion, the comparison is always between the RMS value. So we have to find the RMS value of this current, which is quite easy. Just divide this number by the square root of 2, and it gives you the RMS value of 2.93 amperes. Okay. Now, so we have the, when it comes to total harmonic distortion, we have this part already figured out. This is about 2.93 amperes. Now, we have to focus on the undesired harmonics now. And the whole ratio should be less than 10%. So we have this 10% over here. All right. So you do the math, you have the numerical value for I1 RMS, and it turns out that if I get all of the undesired harmonics in terms of their RMS values and do this math, all of them added together should be less than 0.293 squared. Now, we are making an approximation over here, and the approximation is my assumption over here is there's only one of these undesired harmonics that is making a major contribution in messing things up, and that is my current component at frequency of MF times the fundamental frequency. And actually, I have this numerical example over here to back it up. And if you look at these numerical values that we found, this is relatively small. This is relatively small too. This was the largest one among the undesired one. So if you are only focusing on the undesired harmonics, the component that you have to watch out and be careful about is MF. And that's actually guides us to find the value for MF. All right. So we are making a little bit of an approximation here, but in the end we can be a little bit more conservative and basically compensate for this approximation. So technically, the approximation that I'm making over here is it's really hard to find this. I'm trying to say that this is almost the same as my harmonic at MF, or the harmonic at MF makes the largest contribution, the rest of them are almost zero. All right, so if you make such an approximation, it's very easy. So that sigma of a bunch of terms that we don't even know how to calculate reduces down to just the RMS value of the output current evaluated at a particular frequency of MF times the fundamental frequency. So this now should be less than 0.293, or IMF, remember IMF is, there is a square root involved, has to be less than 0.14, okay? All right, so IMF is what? IMF is the amplitude of the current at harmonic number equals MF. So this is an amplitude thing. Now, how can we find this amplitude? We can find the amplitude of the voltage divided by the magnitude of the impedance, and then we are in business. So instead of IMF, I'm using Ohm's law and replacing it with VMF over ZMF. All right. Now, we have already selected MA to be 0.7. So let's look at this table of 0.7 to find a value for VMF. Unfortunately, Mohan's table does not have a 0.7 column over here. So one way to do that is basically to take the average value of these two numbers. Again, there's a little approximation involved, but we are close enough. Or look at this other table, because this other table had a column for MA of 0.7. And it is telling me that at n equals to MF, I'm looking at 0.92. So basically this table is telling me that, I'll just write it over here. Voltage amplitude at frequency of MF is 0.92 times Vn. All right, so I'm just going to use the same thing over here. There it is, 0.92 times Vn. So we are using the table to get this value of 0.92. What is the value of the impedance? We have to find it basically. So we realize from this inequality that the impedance of the load evaluated at the harmonic of MF should be larger than 333 ohms. All right, so let's see what kind of expression we have the magnitude of the impedance. It was R squared plus the order of the harmonic, which is MF, times L omega squared. We have the numerical value for R, for L, for omega, which is 2 pi 60. All that is missing is MF. So MF should be larger than 14.7. So now it's time to be a little bit of conservative and say, okay, I have made a bunch of approximations, and the indication is I should choose a frequency modulation index that is larger than 14.7. Maybe I should go a little beyond that. For instance, choose MF to be, for instance, 17. To compensate for those little approximations that I made and little components that I kind of neglected a little bit. So, does it make sense to choose MF to be, I don't know, 35? Probably not, because the larger the value of MF is, the higher your switching frequency is, and the higher the switching losses are going to be. So here the indication is an MF of 17 is going to satisfy your customer, because the customer only needs a total harmonic distortion of less than 10%. But if somebody comes and say, I need a total harmonic distortion of less than 5%, then you have to do it again, and for instance over there you find out that MF should be 35. So do not just use a very large MF, because that's not necessarily a good thing. So MF is 17 is almost the smallest MF that satisfies the requirements of the customer. All right. Okay, so we had these two examples, and so if I choose MF to be 17, and just disregard these, so that means the frequency of that triangular waveform that I have to do the PWM based on it should be 17 times the frequency of my reference signal, which was 60 hertz. So we are looking at about this is not kilohertz, this is just hertz. 1 kilohertz of switching frequency, which is reasonable. All right. I think I'm going to stop here. The next topic that we are going to cover on next week is the three-phase inverters. And the sign-up sheet is circulating around.